Swayam Prabha. Digital India. Educated India.
Thank you, Dr. Abhilasha. Good morning, everyone. I am Umair Iqbal. I am a PhD scholar in the Department of Chemical Engineering at IIT Gandhinagar, and I am going to talk about assessing the performance of control room operators in process industries using brainwaves. Let me set up the context first. So, accidents in chemical process industries, they often lead to catastrophes. We have some examples: Bhopal gas tragedy and Texas Steel Refinery explosion. So environmental impacts also because of these accidents. And if you look at safety in the olden days, so there is an operator who is standing in front of a reactor and his job is to monitor the temperature. Now, what can go wrong? So if the operator dozes off, then if the temperature also crosses a particular limit, then there could be an explosion. But what they had is, if you look, the operator is sitting on a stool with a single leg. So if he dozes off, he falls down and he has to wake up. So this is kind of an intervention to monitor his mental state. But now we have a developed field of human factors which deals with understanding the interaction of people with various work elements. And if you look at different aspects of it, there are facilities and equipment design, and there is a safety culture of industries, and then there is important aspect of it, that's the people. And in people, the Health and Safety Executive UK is a top body in chemical engineering, so they have identified top body in safety. So they have identified that managing human error and training and competence, they are the key issues that need to be tackled, and that's what we are going to be doing here. If you look at the nature of human-machine interaction now, so there is a lot of data available because of digitalization, and then there is also automation which often puts the operator out of the loop with the system because there is a shift in role more towards monitoring and diagnosis. So it's necessary to have appropriate mental models which are understanding of the process so that no errors occur. So the mental models, there are inputs, then maybe in the form of alarms or data on the DCS. Then depending upon operator's perception, interpretation, and reaction, they will take certain actions, and based on that feedback, they keep on developing mental models. If there are any issues in mental model, it could lead to misoperation. So there is a need for highly skilled operator as well as advanced and comprehensive performance assessment. So if there are any mismatch between the process demands and human mental capabilities, that leads to cognitive workload and also increase the chances of error. Now, traditional performance assessments, how they have been tackling it, I will summarize it in one slide. So usually it's in the form of number of success and failures, response times, and if there are any standard protocols, whether they have followed it or not, and also on the basis of expert judgment. But these have some limitations. Cognitive aspects are often ignored, and expert judgments, they could be biased. So we adapt a cognitive engineering approach that focuses on looking at the why of the things, like why things are happening. So it includes mental workload, decision-making process, and also the situation awareness. Now, with advancement in sensor technology, it's possible to monitor the cognitive performance of people. So we have EEG and eye tracking. So previous studies we have done using eye tracking. It provides interesting insights. For example, the eye gaze pattern of participants who successfully control a task, it resembles that of the failure group. So that means there is more beyond success and failure that the cognitive metrics are able to capture. And since brain is the center of cognition, we are doing brain-based analysis here. So EEG, depending upon our thought process, neurons get excited and they produce electrical activity, and that electrical activity that can be recorded with the help of a sensor which we call an EEG device. It can be worn like an electrode, and then we analyze the EEG signal. It's often analyzed in frequency domain, especially in these bands, delta, theta, alpha, and beta. And what EEG can capture, there are studies in various domains. For example, theta, it can capture the learning. Then beta and gamma, they can, they are known to decrease with skill acquisition. And also theta and alpha, they are low for high performance. So summarizing that, they can capture both the complexity of the task and as well as the performance. Now we will see how we can use it in chemical process domain to assess mental model mismatch and cognitive workload. So we have a test bed. It consists of a reactor wherein ethene and the reaction between ethene and water takes place, and the separation occurs in the distillation column towards the right. And the task is that if there is a disturbance in the process, you have to control the disturbance by controlling flow through various lines. So with the help of these sliders. So the methodology, so at the same time, during the time when participants are performing the experiments, we record their EEG data. So we have that EEG data at the top, and then we do a window-based analysis, and then for each window we calculate power spectral density, that is we are analyzing it in the frequency domain. So we calculate it for subsequent windows, and if in the next window the power spectral density of theta increases, we say that the workload has increased and the operator is not in control of the process. So I will explain this with the help of an illustrative example. So at the top there is a they start, so initially nothing happens, it's a monitoring phase, and then an alarm gets triggered, inverted red triangle you can see, and then operator generates a hypothesis, takes actions in the form of sliders, so you can see those red lines there, they are slider actions, and he is able to control the process. Now if we do analysis in the action phase, so window 1, window 2, power spectral density is decreasing, you can see in figure C. So that means, and at the same time, what happened to the disturbed variable? If you look at figure D, initially it's within the limits, then it goes outside the limits, then it comes back within the acceptable limits. That is, there is a match between operators' understanding of the process and how the process is behaving. So alternatively, in this case, the operator to control that alarm, so there is an alarm initially. So he is using multiple sliders, as you can see different stem plots with different colors. So he is using multiple sliders. What happens is that the theta starts increasing and then plateaus. So that means at the same time, if you look at these disturbed variables, they go outside the limits and the operator is not able to control them within stipulated amount of time. That results in increase in the mental workload, and we say that the operator is not in control of the process, so and may need interventions. Likewise, there could be instances wherein at times he is in control, other times he is not in control, and overall we could find that our approach can identify around 84% of the cases of high or low workload. That is when the operator is in control of the process or not. And then we are doing training assessment based on EEG. So we conduct similar kind of experiments, but we carry them over a period of 25 days, wherein the operator has to do the same task again and again till he or she learns it. And now we use all the bands rather than one, because there could be correlations between different bands depending upon the nature of the task. So conceptually what we do is we cluster the whole data, 2-second windows, and then see whether it's high cluster, whether it's the cluster that represents high power spectral densities, or it is the low power spectral density. So overall we could identify 2 clusters, and if during a task there is abundance of low cluster fraction, we say that their cognitive performance is better, because we have already seen from the literature that low power spectral densities correspond to better performance. Alternatively, we have poor cognitive performance. So this is the task. We have raw EEG data. It contains some artifacts. We remove the noise. Then we do overlapping to increase the frequency resolution. Then we calculate the power spectral densities on the same basis, and then do cluster analysis, and then see the fraction of the time during which the task is in high or low cluster. Then if it is increasing with the successive trials, we can say the expertise is enhanced, otherwise it's not. So if you look at an illustrative example, so initially the operator is using multiple sliders, as can be seen by different colors of the slider, and so he is not in control of the process, he fails. Same happens with till trial 4, but at trial 4 towards the end he is using the correct slider. So ideally the disturbance can be controlled with one slider, but he is using multiple. And in trial 5 he has stuck with the same correct slider, but he is learning the direction. So the slider, the blue color stem plot, it is going up and down. That shows that he is opening the control valve, closing the control valve, and trying to see the effect of the process. And finally in trial 7 he does things very smoothly, and the time also is less, time taken is less. So the behavior is shown in process and by process and behavioral metrics also. Initially they are not so good, and then with training they improve. And if we look at the cognitive metric, that this CL, our cognitive metric, so it is increasing with trial number. That shows that the performance is enhancing. If we look at the plot at the right, so initially there is an increase in CL, so that is cognitively he is doing better performance, but time and integral absolute abnormality, which measures the overall deviation of process variables, it's not improving. So we can say that this can capture the decrease in cognitive workload and enhancement of training. Now this example is a bit interesting and portrays something different. So trial 3 and initially 3 and 4 he doesn't succeed, but no, sorry, in 3 and 4 he is succeeding, but he is using multiple sliders. So in trial 5 he is succeeding very nicely, like he is taking less time, he is using very less number of slider actions, and so we can say that okay, he has learned. But has he really learned? But if we look at the trial 6, so in trial 6 again he uses multiple sliders, when in trial 6 he could have done he could have clearly cleared the alarm. But if we look at the cognitive metric in this case, so from 3, 4, 5, even if the operator succeeded, the cognitive metric is decreasing, and we saw that in the subsequent trial that he fails after doing that task successfully in the previous slides, sorry, in the previous trials. So the high energy cluster fraction, it can capture absence of learning, which may not be captured by traditional metrics. So if I conclude that we can say that EEG based metrics, they can capture the dynamic workload and match and mismatch within a task, and increase in EEG based low power cluster fraction can capture training levels of operators, and then low energy cluster fraction can also capture absence of expertise. I think that is very important, because absence of expertise is related to the human errors in industry, and that can lead to catastrophes. So overall, we can say cognitive metrics, they can complement traditional metrics, so both are used together. So we will have different, we will have a comprehensive operator performance that is critical for ensuring safety in industries. And oh yeah, if I put this work in the overall context, so we have a human-machine interface, we have an operator interacting with it, there is information flow from the interface, then there is there are operator actions towards the human-machine interface, and we have physiological sensor. In this work, I presented EEG-based analysis, so we can have multiple sensors, they can reveal multiple information about an operator, and then we can do cognitive, we can obtain different cognitive measures and do various kinds of analytics, and that would be given as a feedback. So in this work, it's cognitive workload, but there are other precursors to suboptimal performance other than the cognitive workload. For example, fatigue, that is very critical during long working hours that we see in control room operators, and whether the HMI is also effective. So accordingly, our future work, it is aligned in the same way. So first, we will have multiple sensors, and then we will identify other precursors of suboptimal performance, and then we can also evaluate HMI design based on it. If the cognitive workload by a particular HMI design is more, that means that HMI design is not suitable. On the other hand, if it is low, on the other hand, if the cognitive workload is less, then we can say that the HMI design is better, so we can use it for that also. And we can use these cognitive indicators to estimate the human reliabilities, because currently human reliability, we don't have enough data, and it's primarily done on the basis of expert assessment. Now, if we have objective methods of providing this cognitive aspects of performance, that can go to human factor specialists and human reliability specialists, from which they can integrate it with the overall risk assessment and incorporate human reliabilities in an objective way, which is currently not possible. And we can also develop adaptive training protocols based on the mental state of an operator. So it has been shown in literature that if we follow adaptive training protocols, that means the pace of learning is increasing, and they have often shown benefits. And now the industries are moving towards Industry 4.0, wherein the role of operators is changing. There is a collaboration between humans. Some tasks are taken by humans, some tasks are taken by machine. And so depending upon the cognitive state, the user state of a person, the tasks can be allocated between users and machines. So finally, we can communicate the user state using cognitive aware computing systems based on the integration of sensors like EEG, eye tracking, and other kinds of sensors. Thank you very much.
Yeah, please.
So you mentioned that so after collecting the raw EEG signal,
Yes.
you were just doing some analysis, obtaining the Fourier transform. So you were doing some filtering techniques, or how reliable is the single electrode system? So because we have, if you see in the clinical studies, they use a multiple electrode system. It will be like 64 electrodes, 32 electrodes, and they claim that those electrode systems are robust and they provide accurate data. But what about the accuracy of the single electrode system? Is it more reliable than that?
If we look at multiple multiple electrode-based EEG devices, they may not be feasible in a practical setting because they would cause discomfort for longer hours. Now we have used a single electrode device, and the electrode is placed on at this location, and this frontal cortex, this is known for advanced decision making and things like that. So there is no need to have sensors at other places which are for other which are there for other purposes. But primarily, if it is decision making, how things are going, so that is done on the basis of frontal cortex, and we have that sensor over here. Yeah, and regarding the filtering technique, we are removing if there is any kind of noise. So if it is beyond plus minus 100 microvolts, we just remove it.
Okay, so just a follow-up question. So, so if you are using the frontal cortex, so I think if you are blinking, your eyes are blinking, then it will change the polarity of your EEG signal as well. So, if you remove plus minus 100 microvolts signal, so is it doing removing the blink data as well?
Yeah, some of the blink, because if blinks result in increase in the peak, so some of that data also can be removed. But in one of the studies, we did not remove the blinks because from eye tracking studies, we have seen that even the blinks have been related to the operator performance. Like if they are under stress, there may be more blinks or things like that. And for example, in fatigue also, if a person is fatigued, their blink rate may change. So that also has, that could have some confounding effects as well.
Thank you.
Thank you.
Okay. Any online questions? So just a brief question from me. This is not from technical side, but so given the era of digitization where, all the industries are moving towards digital twins and most AI, ML based models, what do you think these cognitive models have importance, because now the worker's role is no more continuous monitoring and things like that. So what's your motivation? Will continue to be carry over in the future?
I would say there are two aspects to it. So one is like when there are abnormalities in the plant. So human intervention is often required. And if you also look at startups, when the industries are being startup, so those are outside the purview of control systems. So even in those cases also cognitive things will come into play. And the aspect is that sometimes the operators don't trust the automation. So there is a conflict going on between automation and human. So it's very important to assess the humans cognitively around that point, so as to kind of deal with that kind of human machine automation conflict. So I would say that this is necessary.
Okay, because the next PSC's title is around IoT 4, which has one perspective of robotizing the industrial processes instead of humans placing robots in the future. So that's why I asked this question, but good answer.
Yeah, even if the robots are there, that robots will have to interact with the humans. So then, as humans, we know what is if I am dealing with a client or someone, I know what's there based on their facial expressions or their state, I will be communicating accordingly. So robots will also have to assess the human state and accordingly deal with them, how they want to communicate with them. So even in long term, maybe few years down the line, that will have importance.
Good. Thank you.
Thank you very much.